Assalamualaikum and hello to everyone. So we meet again in another example for chapter 3, okay, involving the steady flow energy equation. So our component today is the compressor, okay, but only the substance right now is a helium gas, okay, so you can pause to read and understand the question properly. Okay, so we have a compressor, okay, which substance is helium gas. Okay, initial pressure is 105 kilopascal, initial temperature is 295 Kelvin. Okay, compress at the exit, pressure increases to 700 kilopascal, temperature increases to 460 Kelvin. There is a heat loss. Okay, heat loss here refers to Q out in units kilojoules per kg. So 15 kilojoules per kg. This is the Q out. Okay, in small letters. Okay, because why? Because of the unit kilojoules per kg. Okay, during the compression process, the mass flow rate in units kilogram per minute is 60 kilograms per minute. Okay, so we have to convert it into kilograms per second. Now we can neglect the changes in potential and also kinetic energies. So for the first item, we have to find the volume flow rate. Okay, and the second item is the work input to the compressor. So given in the questions are the specific heat at constant pressure Cp and also the gas constant for the helium gas. Okay, so the answers are given in the question also. So let's try to solve the question, but first let's try to write the conditions. Okay, so we know it's a compressor, so work out is 0. Okay, and then we have heat loss, so heat added or heat Q in is 0. Okay, Q out is available, so we cannot cancel Q out. And then we can neglect changes in kinetic and also changes in potential energy. Okay, so these are the conditions. Okay, so let's try to draw in step 1 the schematic diagram for the compressor. Okay, so we have a compressor. Let's say here there's a shaft which will rotate, producing the work input. The inlet is at the bottom, state 1. The outlet is at top, state 2. Okay, so we can write the properties. So we know at state 1 the pressure is 105 and temperature is 295. Okay, so at state 1 P1 is 105 kilopascal, T1 is 295 kilopascal, Kelvin. And we also know the mass flow rate. Okay, so mass flow rate in units kilogram per minute is 60, but we have to convert. Okay, so minutes to second we have to divide by 60. So we have 1 kilogram per second. Alright, then we have at state 2, okay, the pressure of 700 kilopascal and also temperature 460. Okay, so 700 kilopascal and temperature at state 2 is 460 Kelvin. Okay, don't forget our heat loss. Okay, so heat loss to the compressor, so there will be a Q, all right, in small letters because of the unit is in kilojoules per kg. Okay, so to convert into capital letter Q, so this will be m dot multiply with Q out. Okay, if we want to convert it into capital letter Q, we have to multiply it with the mass flow rate. Okay, so should not be a problem later on. Okay, so next we'll try to come up with the equations. So for step 2, the first item is the volume flow rate. Okay, so Mass flow rate is given, and we know the relationship between mass flow rate and volume flow rate is given by the following equation. So we can rearrange. Okay, so this property is the property at state 1. Okay, the specific volume at state 1. Okay, and next, is to for the work input to the compressor. So number B, SFEE. So we have the general equation. Okay, inlet equals to exit Alright, so we can cancel based on the conditions. So we know that Q in is 0. Okay, kinetic and potential energies can be neglected. Q out is available, work out is 0. Okay, alright, so write what is left. So we have on the left hand side, okay, on the left hand side we have the work input, the enthalpy. On the left hand side, on the right hand side we have the heat loss, okay, and also the enthalpy. So to find for work input, we rearrange the equation. Okay, so we can get okay, so this is the equation for work input, but remember the substance is a gas, so H here is replaced with CPT. Okay, so replace H with CPT, so we can get the equation. Okay, so because of gas, we have to replace H with CPT. Okay, next is to find the properties. Okay, so for step 3, okay, so at state 1, we know the pressure, okay, 105 kilopascal, and the temperature is 295 Kelvin. Okay, so we have to find for the specific volume. So using the gas equation, okay, so we can rearrange. Okay, so R is 2.0769. Okay. 2.0769, temperature is 295, pressure is 105. Okay, so we can get the answer here. Okay, 5.8351 meter cubes per kg. Okay, so at state 1, we have done. Okay, state 2 now. Okay. State 2, if I'm not mistaken, we don't have to find any properties, so we still can write it down. So pressure 2, if I'm not mistaken, is 700 kilopascal, and temperature 2 is 460 Kelvin. Okay, don't have to find anything, but still we can write it down. Okay, so for step 4, we just have to substitute. Okay, so for the first item is to find the volume flow rate. So volume flow rate is equal to mass flow rate multiplied with the specific volume. So mass flow rate is 1, specific volume is 5.8351. So we can get the volume flow rate. Okay. Okay, so next is to calculate the work input. So we have the equation just now. So work in equals to Q out plus the mass flow rate Cp T2 minus T1. Okay, so Q out, remember, we have 15 in units kilojoule per kg. So we have to multiply with the mass flow rate. Okay, so the mass flow rate is 1 here. And then for Cp, for helium is from the question 5.1926. Okay, 5.1926. Okay, so here 5.1926. Okay, change in temperature 460 minus 295. Okay, so I will calculate it here. So the work in here will be 460 minus 295 times with 5.1926. Okay, times 1, and then we plus with 15 times 1. So we can get 872 kilowatts. Okay, so this is the answer. Okay, so this is for this question. So thank you. I'll see you in another video, another example. So thank you.